Good morning, everyone. Welcome back to Organic Chemistry 1. Today we'll be doing Lecture 12 over um, addition reactions of alkenes. We'll be doing that for the next couple days. And then starting on Wednesday, we'll do alkynes. We'll finish up alkynes on Thursday. And then Friday will be your fourth exam. We're going through this really fast. And the summer session for this class is almost over. I can't believe how fast we're going through this stuff. Just so you know, though, at the time of this recording, I have not gotten all the exam results yet. It's still going on right now. But rest assured, there will be a exam solutions video posted, as always, so you can gauge how you did overall with any adjustments I make and such. So, yes. Just also a reminder, too, not only do you have your fourth exam on Friday, you also have your final exam in the class, like completely in class, next Thursday. So we're getting pretty close to that. The 3 chapters that lead up to the final exam are, one of them is kind of long, but I'll have to cut it short a little bit so that we can fit everything. But other than that, I mean, we're almost done, so just hang in there with me, right? Okay, so today, Lecture 12, we're talking about addition reactions of alkenes. We're going to talk about those for a little bit longer, okay? Let me switch over to the correct view, and then we can get started. All right, so there's some common types of reactions that happen with alkenes, and one of them is called the addition reaction. And quite simply, the addition reaction is the opposite of an elimination reaction, right? Where you have an alkene, like you see here, okay, and you add X and Y. Generally, X and Y are a hydrogen atom and an alkyl halide. I'm sorry, not alkyl halide, but a halide, right? And you get them adding across the double bond, like so, right? The pi bond is converted into 2 new sigma bonds. Okay, so there are a few different types of addition reactions that you see here, and we'll go through them, in the next lecture or so. We have hydrohalogenation, we have hydration, right? Hydrohalogenation is what I was just speaking of before, where you have a halide, with a hydrogen being added. A hydration reaction is quite literally a water being added across the bond, like the components of a water being added. Hydrogenation, 2 hydrogens being added. Okay. Halogenation, where you have 2 halides being added. Halohydrin formation, right? So we have a halogen and an alcohol being added, and then dehydroxylation. Sorry, not dehydroxylation. That made it sound like you're removing a hydroxyl group. It's dihydroxylation, where you're adding 2 hydroxyl groups. So we'll go through each one of those in time. So how does this work? You have a pi bond, and it acts as an electron pair donor, right? So literally, as a base, the double bond, one of the pi bond comes over, pulls off a proton, right, from an acid, and the electrons from that bond between the proton and the acid go to the acid, and you get its conjugate base, and you get a carbocation, right? Notice that it's a tertiary carbocation, right? And so then you can have the halogen, or the halide, do a nucleophilic attack on the carbocation, the tertiary carbocation. You can also use it as a base, right? You can also use it as a nucleophile, the double bond, right? The pi bond. And the nucleophile can do a nucleophilic attack on an electrophile, right? And then you have the electrophile attached there on one side of the double bond that used to be a double bond, and then you again have a tertiary carbocation there. Okay. So there's some naturally occurring acyclic alkenes. We have allicin here, which is responsible for the odor of garlic. We have geranol, isolated from roses and used in perfume. We have farnesene, farnesene. I guess that's how you say that. Found in the waxy coating of apple skins. We have limonene, which is for the strong smell in oranges. Pinene, alpha pinene, from pine resin, and it's a primary constituent of turpentine, which is paint thinner. Of course, we have cholesterol, right? The big. Remember, I told you guys it's like 6, 6, 6, 5, right? Which is the normal structure, like main structure for a steroid, right? So we have cholesterol here. We have muscular, a sex hormone that is in the house, common to the housefly. Interesting, I didn't know that. More farnesene. No, that says famcene. Famcene? Wait, was the other one farnesene? Yeah, that one was farnesene. And this one is famacene, I think that is. Anyway, it's an aphid alarm hormone, right? There's ectocarpine, right? A pheromone released by the eggs of the Ectocarpus cilius to attract sperm cells, the seaweed. Interesting. And then here we have the 2Z6E 3-ethyl 7-methyl deca 2,6-diene 1-all. And you can't see it because my head's in the way, but that was a complicated name for that was a complicated name right there for a sex hormone of the codling moth. Wow, fun times. Bring myself back there. So, there again, this continuation here of alkenes in nature and industry. We have precursors, right, like petroleum, and petroleums can be distilled down into ethylene and polypropylene, right? And you've heard of polypropylene before. That's a plastic. That's the plastic used in all Tupperware and things like that. So alkenes are the critical precursors in the chemical industry. Each year, over 70 billion pounds of propylene or propene and 200 billion pounds of ethylene or ethene are made from cracking petroleum. How interesting. So here you can see all of the natural, all the petroleum products that come from petroleum, of course, but then also from ethene and propylene, right? Which you get polypropylene, which I already mentioned before, right? We use that in plastics, like our Tupperware containers are made of polypropylene. If you didn't know, you can actually flip over the bottom of a Tupperware container, and it will say at the bottom in this little triangle, which has got the little number in it, for recycling, right? The hardness of recycling, and then under it will say PP, and that PP stands for polypropylene. I actually have some. I was building some Legos on my desk the other day, and I have some tubs here from that. And see if it has it. Yeah. See, if you see, you can't really see. This isn't even polypropylene. This is there's a triangle right there. Let me maximize. There we go. Can you see the triangle right there? Right there, yeah. You can't really see it because it's like so clear, but there's a little triangle right there, and it's labeled 1, and it's actually labeled PET, which is polyethylene, right? So this is a different plastic. I wonder if that's actually even listed on here. Oh, there it is right there, polyethylene. So that's let me come back. See, polyethylene is what this is made of right here, right? PE for polyethylene, right? I really want to show you PP though. Oh, I have another container over here. Let me see. Hold that thought. Here we go. So we actually had takeout the other day, and I don't know why, but I specifically really like these containers here because they work really well in saving leftovers when you have a small amount. So I always save these containers and put them in the dishwasher because they work really well. But this actually does say it. Let me maximize my head again. There we go. And if you look and see, focus. Ah, there we go. I just need to have the right lighting. But right there, there he goes. There's a triangle with a recycling sign with 5 around it, and it says PP at the bottom. So this is made of polypropylene. So yeah, I was telling you how Tupperware is made of polypropylene. Chemistry all in your life, everywhere. Isn't it crazy? Right? Crazy. Anyway. So ethylene can be made into polyethylene, like I was talking about here. This plastic here is polyethylene. It's a little bit more clear. Also, of course, ethylene can be made in ethanol. We can drink that, but I wouldn't want to make it. I wouldn't want to drink ethanol that came from the distillates of petroleum. By the way, we've discussed already in a previous lab how I would make ethanol. So I would. This is probably the ethanol you would use to clean stuff. The stuff I was talking about before that they distill with like denaturants and stuff. There's ethylene dichloride, acetaldehyde, ethylene oxide, ethylene glycol, acetic acid, of course, right, which is vinegar, polyvinyl chloride, which is PVC, like PVC pipes in your plumbing, and then vinyl chloride, which is like is what vinyl gloves are made of, actually. You know, like the not hand washing gloves, the dishwashing gloves, not nitrile gloves, like the examination gloves, but they're yellow colored, and you put them on, they come down to here, and they're kind of loose, and you use them to wash dishes. That's polyvinyl chloride. I mean, that's vinyl chloride, right? And then again, propylene. We already talked about polypropylene, isopropyl alcohol. We used a lot of that during the pandemic, didn't we? In fact, I was telling you a while back that I did a lot of 3D printing, and one of the parts of 3D printing is post processing your 3D prints by washing them with isopropyl alcohol. Well, let me just tell you, during the pandemic, everybody wanted to do 3D printing because no one could go anywhere, but then there was no isopropyl alcohol anywhere to clean your freaking prints. So that was a good time. Acetone, of course, nail polish remover, propylene glycol, propylene oxide, and cumene, which I have no idea what cumene is. If you know what cumene is, post it in the comments below if you're watching this on YouTube. And then I wanted to, this was actually a little bit extra I added in here because I really wanted to talk about this too. I think you can see the whole thing even with my head there. So there's also tons of medical kind of applications to alkenes too. And what you actually see here on this side, on the first structure you see, is a molecule called bilirubin. And I believe that's how you spell bilirubin. And bilirubin is actually, whenever babies are born, and I remember when my brother was born, he was a little jaundiced and he looked a little yellow in the face, okay? And so when babies are born, they have this buildup of this molecule called bilirubin, right? And that bilirubin is actually yellow colored, and so the reason why it happens this way, where you have this bilirubin and babies are yellow colored, is because there's a buildup of it. And what happens is that generally this bond right here, right, this alkene bond right there, right now it's in the Z conformation, right, or Zusammen, right? The highest priority substituents are on the same side right there, and Z for Zame, as they would say, right? And the problem with that is that when it's in that configuration, a lot of the things that are like that would do hydrogen bonding, like this alcohol and this carbonyl oxygen, or these amines with these carbonyl oxygens right there, right? They do hydrogen bonding with each other, right? They do hydrogen bonding with each other, and that's a problem. And the reason why that's a problem is because when they do hydrogen bonding with each other, it makes it so that bilirubin isn't quite as soluble in water, right? And so when it's not soluble in water, it builds up, right? Babies can't pee it out, or you can't excrete it, and so you have this buildup of insoluble bilirubin, and that's why you get jaundice in the skin. Your skin turns yellow, right? And when you generally what happens is that you have to have a developed liver for you to be able to actually turn this bond into an E, right? An integer, right? Where it switches so that the two, if you remember what the difference is between E and Z, right? The two highest priority the two highest priority substituents are opposite each other, right? So if you can see here, the two highest priority groups is the nitrogen and the carbon right there, and they're on the same side, right? And so there's an enzyme in your liver when you have a developed liver that can switch it, right? Can do an isomerization of that alkene, right? So that then the carbon now is down here, and let me actually just erase all this stuff so I can write down there, right? The carbon comes down here now, right? And then the rest of the molecule is there. And then over here now is the proton that used to be where the carbon was. And now the two highest priority groups are separated from each other, right? They're opposite each other, right? The carbon's down here and the nitrogen is up here. And so now it's a E, right? It's an E configuration, right, of bilirubin. And the thing about that is that when it becomes an E configuration of bilirubin, all these hydrogen bonding capable atoms over here are moved so that they're on the outside and they can't hydrogen bond to each other anymore, which makes them exposed to water, and water can dissolve them now. They're more soluble to water now, right? So the way that this happens then in babies is that since they don't have a developed liver so that they can actually process the bilirubin, what they do is that, and they did this to my little bro, they gave him little tiny sunglasses, cute little sunglasses, and they put in his incubator, and he was actually prematurely born too, by the way. But now he's like taller than me. It's kind of crazy, my little brother. but and they put him in these incubators, with little cute little sunglasses, and they have lights shining on him, right? And the light actually can do a photoisomerization, right, and change this what is a Z right now, right, alkene into an E alkene through photoisomerization, which is super cool, and that's how they kind of treat jaundice in babies, right? So who would have thought like having just a Z or an E alkene made such a difference in babies' lives, right? E means you're going to have jaundice. I mean, not E. Z means you're going to have jaundice, right? Because those highest priority substituents are on the same side, but that also means those hydrogen bonding atoms are hydrogen bonding to each other. So you want them flipped so that they're exposed to the water, and then they're in the E configuration, and in the E configuration they can be dissolved for water because they're much more soluble that way. So that's really neat. Oh, those alkenes, okay? So the other example over here I wanted to talk about, especially for you guys that are going to med school, right? Well, I guess the bilirubin thing is a med school thing too. That's the reason why I added these two in there, because I know a lot of people are in organic one because they're getting like pre-med and medical school prerequisites. But here we have a molecule called, this one up here is called cis-retinol. Right, cis-retinol. Actually, it's 11 cis-retinol to be exact. And what it is that it's a molecule, a cofactor, that's in your rods and cones. Or not just rods, not rods and cones, but rods. So if you didn't know, the pigment in your eye, right, are composed of rods and cones. And I actually learned this from Bill Nye the Science Guy, right? Not the chemistry part, but the part about rods and cones. And so rods are responsible for you being able to see light, okay? And so the rods are called rods because they are composed of a part of the main part of rods, the actual rod cells, right, is a protein called rhodopsin. Okay, and the rhodopsin, you know, functions in there, right, in your rod cells, along with the cofactor cis-retinal, right, cis-retinal, and then when you have light, and this is a huge simplification because you can go way deeper into the signal transduction and the biochemistry and the anatomy and physiology of it right here, but I don't want to spend my entire lecture talking about that, so because it can be a whole lecture. But basically, what happens is that light comes in, right, and it hits this cis bond, right, this cis alkene bond right here, right, pi bond. And when it does that, it does another photoisomerization, just like in bilirubin, making it trans. So this is called all trans retinal, right? And when that happens, it allows you to see light, if you didn't know, right? So it's pretty cool how much chemistry is in life. You just learned a lot about plastics, and you learned about being jaundiced and being able to see light, right? Just so you are aware, right? If you're not aware, if you didn't have this, you wouldn't be able to see light. You wouldn't be able to see in the dark, right? In fact, this kind of interaction, or this kind of reaction that occurs is what allows you to have night darkness, no, night vision. There it is, night vision. So alkenes are super important. But let's just get into the chemistry of it now. I just wanted to make sure you knew how relevant this stuff is. So first thing, as always, when we learn about new types of molecules, we got to learn how to name them. Last time I was naming alkyl halides. This time it's going to be naming alkenes, right? So alkenes are given IUPAC names using the same procedure as alkanes with minor modifications. Step 1, identify the parent chain, as always, but the parent chain must include the double bond. That's the big thing, okay? And then identify the name of the substituents. Then 3, assign the locant and prefix, if necessary, to each substituent. Give the double bond, right, the carbon-carbon double bond, the lowest number possible. Kind of like the way we name substituents, right, with the lowest number possible. The way we number substituents, we give them the lowest number possible. And then list the numbered substituents before the parent name in alphabetical order. Ignore prefixes except for iso when ordering it alphabetically. Okay. So that's, remember, prefixes like tert, that kind of thing, like tert butyl. And then the carbon-carbon double bond locant is placed either just before the parent name or just before the -ine suffix. Okay, the -ine suffix. And let me show you what I'm talking about. So first step, identify the parent chain, which must include the carbon-carbon double bond, right? So here we have pentane as a contrast here, and then we have pentene right here, right? And we name it -ine because it's got a double bond in it, okay, instead of pentane. But the parent chain here, if you have more than one, must include the carbon-carbon double bond, right? So previously the parent chain in octane here was the longest one here, right? But here the parent chain is going to be the one that has the double bond in it, right? Even though it's not the longest one. And so that's why the parent here is heptene, right? Heptene, not octane. Next, identify the name of the substituents, which we already know how to do that. And then assign a locant, a prefix is next to each substituent, and give the double bond the lowest number, right? So again, over here, we want the double bond to have the lowest number, so it's going to have 2. We don't want it to have 6, right? And then, of course, over here at 5, we have dimethyl. Here we have 6-methyl. And then, yes. So actually it would be 5-6, 5-dimethyl, 6-methyl heptene, right? Or you could name it this way, the way they have it, trimethyl 2 heptene. um, list the numbered substituents before the parent name. Oh, I skipped ahead and I didn't even realize it said to list the number of substituents before the parent name in alphabetical order, and then ignore the prefixes except for iso. And then 5, the double bond locant must be placed either just before the parent name or just before the ene and suffix, the ene suffix, right? So here we go. We have 5,5,6 trimethyl 2-heptene, or 5,5,6 trimethyl hept 2-ene. I kind of prefer that one more. That sounds better to me. Okay, so forget what I said a couple seconds ago. Note note this alkene is an E configuration. Okay, which must be indicated in the name, in the parentheses, right? So that's going to be E5,5,6 trimethyl 2-heptene or heptene. I like to say 2-heptene, but they have hep2-tene here. Oh, ene. That's hard to say. Yeah, just go with this. So 5,5,6 trimethyl 2-heptene. Okay, that's easier to say than hept2-ene. That's really rough. All right. Now that we had a little crash course on naming heptenes or teens or alkenes, right? I needed it too. I'm so once you get deep in the game here in chemistry, you start naming things the common names, and you just don't even remember how to do IUPAC anymore. I'm being honest. Addition and elimination reactions are equilibrating reactions, right? So we already talked about elimination reactions before in the previous chapter, right? But it turns out that it depends on equilibration, right? The side that it's favored depends on the temperature, and my dog is having a nightmare or something. Kiara, you okay, girl? Okay, she's okay. She's fine. You all right? Yeah, okay. She does that a lot. I feel like when I rescued Kiara, and so I feel like her previous owners were not very nice to her. She's very skittish. When she first got here, she was really skittish. Now she's super loving, but she still has these nightmares, and it's very sad. So, sorry. Back to this. Addition and elimination reactions are equilibrating. Addition and elimination reaction. I promise I can get through this. Addition and elimination are equilibrating reactions, right? Okay, that's where I was before. Which side is favored depends on the temperature. Okay, and so here we have our alkene, and we have an acid that can act as our reagent, and then so you can either go addition. You can either go addition, right, where you add on both sides of the alkene, like I was saying before, or you can do elimination, right, where you get the alkene and you lose the leaving group and a proton. Okay. So here's the phrase you need to remember. The higher the temperature, the more important entropy becomes, right? And so that's why this here, right? Remember in our delta G equation, temperature is in the entropy term, right? The higher the temperature means the bigger the entropy term. Okay. Addition reactions are favored by enthalpy, right? So sigma bonds are stronger and more stable than pi bonds. Okay. So we have here where we are breaking a bond here, and it takes 63 kilocalories per mole to break that bond, and we takes 103 kilocalories per mole to break that bond, which is a total of 166 kilocalories per mole, right? And then when we form bonds, these bonds here, forming the hydrogen-carbon bond there is 101 kilocalories per mole, and then forming a lot of C words, forming the carbon-chlorine bond is 84 kilocalories per mole, which gives you 185 kilocalories per mole. So of course you already know this from previous lectures, right? The delta H, right, the enthalpy, is equal to the bonds broken minus the bonds formed, right? So that's 166 minus 185, which gives you 19, right? So we know that's an exothermic reaction, negative 19, right? It's going to release some energy. Let's keep on going on this line of thought here, right? Just a quick review, just a quick thing here, right? This is entropy, right? Delta S is entropy. But right now, over here, we're talking about enthalpy, which is delta H, okay? And we have negative 19 kilocalories per mole as the net delta H there, okay? Addition reactions are not favored by entropy, okay? Two molecules combine to form one product. That means the entropy decreases, which makes sense, right? Because when you go from two molecules, right here, to making one molecule, you're actually increasing order, right? Going the other direction would be increasing disorder, and that would be more entropy, okay? But going and making one molecule out of two molecules decreases entropy or decreases disorder, right? One product is less disordered than two reactants. Two reactants, right, are more disordered, right, than one product. So, to bring it all together, right, a lower temperature, enthalpy dominates, and addition reactions are favored. Okay? At higher temperatures, entropy dominates, and elimination reactions are favored. Okay? So these are the things you need to remember right here. Okay? So here's a cute little drawing here to bring it all together, right? At lower temperatures, we go from two reactants to one product, right? Which is the addition reaction. But then at high temperatures, we go from one product to two reactants, which is the elimination, right? I better just write that in there so you guys remember. Addition, right? Over here is the elimination. Okay? Therefore, lower temperatures are typically used when doing addition reactions. Okay? Again, remember that. These are important right here. Okay? So, first type of reaction we want to talk about is the hydrohalogenation reaction, which is the addition of HX, right, to an alkene. And you can use HCl, hydrobromic or hydrochloric acid, or hydrogen chloride, right? Hydrogen bromide or hydrogen iodide, right? So we have here an alkene. Right? And we have here hydrogen bromide, and notice the temperature is minus 30 degrees Celsius. So if you didn't know this already, your freezer is around minus 30 degrees Celsius. It's actually minus 20 degrees. So when we did this reaction in the lab, we would put it into a freezer, right? You could use things like dry ice too. And so here we're going to have an addition reaction, okay? We're going to have an addition reaction. Quite simply, like this, right? Like this, right? And then BR is by himself now. Or maybe it's herself, or themself. There we go. Okay? And then so you're left with the carbocation over here. There's already a proton added right there. And you're left with a carbocation right here. And then there's a nucleophilic attack, and that's how you get 76% of that product. Okay? Oh, forgot to put in the R for bromine. There we go. Sorry. If the alkene is not symmetrical, then there are two regioisomers possible. And depending on which of the carbon gets, and that's depending on which carbon gets the proton and that depends on which, let me say that again. If an alkene is not symmetrical, then two regional isomers are possible. Depending on which carbon gets the hydrogen atom and the which one gets the X or the halide. So this is just showing you where they're going to be adding right here, right, where the green parts are, right? And so it's asking you then, where are the X's going to go, here or here? Which we will see in the next slide, right? So this is going to be the introduction to Makarnikov, and he's a famous guy, right? And we'll talk a little bit about him in a second. But hydrohalogenation is regioselective for what we call a Markov-Markov addition. Okay, so in 1869, Markov-Markov observed the hydrogen atom tend to add to the carbon bearing the more hydrogen atoms, right? So if you see here, right, and it's kind of small. I don't know why it's so small on this slide, but we have again here at the vinylic positions, okay, here and here. This side had a hydrogen atom, and this side does not have a hydrogen atom, has two methyl groups, right? So when we did our addition reaction, the hydrogen right here that was from the hydrogen bromide gets added here to the side with one hydrogen atom, right? And not to the side that was more substituted with the two methyl groups. That's where the bromine is going to go. So that is called a Markov-Markov addition, right? That's called a Markov-Markov addition, and what it says, what Markov-Markov addition says, is that hydrogens will be added to the less substituted side, or the side that has more hydrogens already on it, right? And then in turn, the halide will be added to the side that's more substituted, right? Halogen is generally installed on the more substituted carbon, right? More substituted carbon. I don't know why this picture here is so much bigger than this picture. There's room for me to actually expand this, and I didn't expand it, and I apologize. I'm sure you can read it, though. So interestingly enough, though, if you do this reaction in a peroxide, like some kind of acyl peroxide, right, you actually get the opposite. You actually get the opposite, where the hydrogen gets added to the side that's more substituted, and the bromine gets added to the side that's more less substituted, right? The one that has more hydrogens on it. And so that's called the anti-Markov-Markov addition, right? So just know that if you do an addition reaction in some kind of peroxide, okay, some kind of peroxide, you're going to get the anti-Markov-Markov addition, right? Hydrogen on the side that's more substituted with the two methyl groups, and then bromine on the side with the two protons right here. Okay? Interesting, right? So what that means then is that the reaction mechanism must be different when there is a peroxide present, okay? When there's a peroxide present. And I'll tell you now that whenever you have a peroxide, sometimes it's, more often than not, it's going to be a radical mechanism. Radical, right? Radical. Super rad. Right, where it's not pairs of electrons moving, but a pair of electrons will split up into one electron each, and then they will move. And don't worry, we'll talk about radical reactions later on in the semester, which is not that much longer away. So look forward to that. Put a pin in that, okay? We're not going to go over the radical reactions now. So the important lesson here is that regioselectivity can be controlled, right? If you want to get the Markov-Markov addition, right, where the bromine adds to the more substituted side, right, then you're going to do the HBr addition with no peroxide. But if you want to have the anti-Markov-Markov, where the bromine is added to the side with the more hydrogens on it, right, the less substituted side, you for damn well sure will be making this reaction being done in a peroxide, right? With some peroxide present, okay? Some peroxide present. So before we go to this conceptual checkpoint, I just wanted to say it's an interesting story about how Markov found this out, right? They were doing all these experiments, and it was like, okay, it's doing Markov-Markov addition before it was called Markov-Markov addition, where the bromine was going onto the side with the more substituents and the hydrogen was going on the side with the more protons or the more hydrogens, right? But then sometimes it wouldn't work. It worked most of the time, but then sometimes it wouldn't work, and they couldn't figure it out, right? So many researchers couldn't figure out what was going on. It turned out that what was going on was that they were doing their reactions, okay, and if their reagents were pure, right, then they would get the Makarnikov addition, right? But then, if they were doing their reagents and if they were doing the reaction and the reagents were not pure, I mean, just trace amounts of an alkyl peroxide, just trace amounts, right? It would be pushed to be doing the anti-Markovnikov reaction, right? So that's a story in how important it is to have pure reagents, right? Or as pure as possible. Okay, as pure as possible. Okay, so we have here in our conceptual checkpoint, right? Let's just do this together real quick. Okay, we've got our alkene here. Okay, and there's no peroxide there, so it's going to make the Markovnikov product, right? The not the anti-Markovnikov, but the Markovnikov product. Okay, and so the Markovnikov product here is going to be not that, because that's got like 2 more carbons than it's supposed to. Erase. Try that again. I'm having trouble drawing my pentanes. My cyclopentanes is what it's about. There we go. Okay. And then there we go. I almost forget the R in bromine, which is bad because B by itself is boron. You don't want to be confused with those two things. They have very different electronegativities, right? Right. So quite simply, what happened here? Right, I had a proton there. Okay, had a proton, and we do my addition reaction here, and lost my train of thought. Oh yeah, comes over here, pulls off the proton. Okay, then you're left with this cool little tertiary carbocation right there. Okay, and then my bromine. I didn't forget the R this time. Okay, comes over, does nucleophilic attack right there, and that's how I get that. And that's my Markovnikov product, MA for short. Markovnikov addition. Audition? Is he auditioning for like The Voice or something? No, addition. And then here we have the peroxide. So we know we're not going to do Markovnikov here. We'll do the anti-Markovnikov here. And so that's pretty simple, right? Because we know over here the less substituted side is this one because there's 2 protons there, right? And here we have substituents there, right? So again, we'll do our little thing here and pull off this proton here, and then we'll kick off the bromine, and then we'll get this bromine minus charge, right? We'll come over and pull off this proton right there, right? Why is it doing that? I have no idea why it's doing that. It shouldn't be pulling off a proton at all. It should be doing a nucleophilic attack on this carbon here. You see what happens when you skip steps when you're drawing these things, right? Anyway. Don't skip steps when you're drawing your reactions, because then you make a mistake like I just did there, right? It does a nucleophilic attack right there, right? And that's why we get this guy here. Okay, that guy there. Not only that, I put 2 hydrogens here. Why did I do that? There we go. Sorry about that. I made the mistake of having 10 electrons on 1 carbon just now. See, so don't feel bad. Everybody makes mistakes. And this is the anti-Markovnikov, also known as AM for me. Oh, of course, as always, the next slide has the answer on it, right? So again, you saw here, right? This is the Markovnikov, and this is the anti-Markovnikov, because this one has the peroxide. So for more practice, right, do 8.6 an 8.5, which you can't see because my head's blocking the way, so I'll show you that real quick. Right there, right? 8.5, 8.6, Wiley Plus. Good luck to you. So let's go through real quickly again, I already went through the mechanism with you on the previous slide, but we'll do it again because I don't know about you, but the more practice I get, the better, right? So the mechanism is 2 steps in the hydrohalogenation. Okay, the double bond comes over, pulls off the proton, and then the bromine receives those extra electrons. And then bromide rather, comes over, does a nucleophilic attack on the carbocation, that tertiary carbocation there, and that gives you our product. Oh, I just got a little cramp in my chest. Ouch. And this is our MA, right? Our Markov addition. Pretty simple. Pretty simple. Yeah, MA, because notice that the bromine is here along with another methyl and another methyl here. The hydrogen is here along with just another hydrogen there and a methyl. So the more substituted side is getting the bromine, the more the less substituted side is getting the proton. That being the well, yeah, it is a proton. Okay. So let's look at the energetics of this particular reaction. Okay. The step with the highest activation energy, right, also known as the rate determining step here, is the formation of this carbocation right here. Okay, that means that proton transfer right here, right, is the part that takes the most energy to get you there, right, to get you to that part of that carbocation. But then after the proton transfer, you get the nucleophilic attack, and it's downhill from there. And as you can see, it's going to be a spontaneous reaction right there because the lowest energy, thermodynamically spontaneous, because the product's potential energy is way lower than the reactant's potential energy. But of course, again, that's based in part on the temperature of the reaction. Okay, so again, we have 2 pathways when it comes to these kind of things, these addition reactions, right? Recall that there are 2 possible products, the Markov product and the anti-Markov product, right? Again, the Markov pathway is this one here, and then you have the anti-Markov pattern, which is in here. And the reason why the Markov product is formed normally without the presence of if there's no peroxide present, right, is because when this proton transfer happens, right, you get a tertiary carbocation right there, right? And so the carbocation stability, right, plays a big part in having a Markov product. And you can see that here, okay? The red line here is a tertiary carbocation, and its energy, okay? And here is a secondary carbocation, which would be formed if you had the anti-Markov product. And you can see that the potential energy, right, for a tertiary carbocation for a Markov product is much lower, right? Therefore, it's a faster reaction. Okay. Again, Skill Builder 8.1, drawing mechanisms, HX. Skill Builder on Wiley Plus. I hope Wiley Plus has been helping you. I mean, I plug it all the time, but and I like it. I hope you guys like it too. Let me know in the comments below if you're watching this on YouTube if you like Wiley Plus. I'm also teaching Organic 2 in the fall, right, here at TCC, and I'm considering doing, using Wiley Plus again, maybe. But if you don't like it, I won't use it. Are any of you taking Organic 2 in the fall at TCC? Because I'll be there with you. And it's going to be our first time since the pandemic that we actually be in class together again. Good times. Okay. So hydrohalogenation may result in the formation of a chiral center. Okay. And so here, of course, we have HCl as our addition reagent. Okay. And of course, when the chlorine gets added right there, we have a proton there, and methylene group, methyl group, and a chlorine. So that's definitely a chiral center. But the great thing about this, though, in contrast to the alkyl halides, is that in a Markovnikov addition, two products are formed in this reaction, but the two enantiomers are equal amounts of both enantiomers, R and S, right? So you don't have to pick the major product here. There's no major product in this type of thing right here because the both of the enantiomers are produced in equal amounts. And you'll see some other stuff that's going to be a little bit simpler here than it was in the alkyl halides, because the alkyl halides had like the regioselectivity, it had the stereospecificity, the stereoselectivity, right? It was just, there was a lot of figuring that kind of stuff out. This should be a little bit more, I think at least, a little bit more easy to remember. So the carbocation intermediate can be attacked from either side, right, of the empty p orbital, and that's why you get equal probability of R and S, right? There's no SN2 backside attack here that causes inversion. And the reason why is because the nucleophile can attack from both sides of the empty p orbital. Good stuff. Conceptual checkpoint, 8.9. Predict the products. Wiley plus again. Okay. So, if you recall, though, back in the alkyl halide section, right, carbocations like to do rearrangements to become more stable, right? So recall that carbocations can rearrange, hydride shift or methyl shift. I don't like it when they say that. It's a methide shift. Okay, methide shift, if they can become more stable, right? So, take a gander here. We have this double bond coming out to deprotonate the chlorine, okay? And so now we have that proton over here. So now there's 3 protons here on that particular carbon, okay? But then we have a secondary carbocation. So what's going to happen, right? Well, there's a hydrogen right there, atom right there, and there's going to be a hydride shift. So now that the hydrogen is over here, as you can see, and that leaves you with a tertiary carbocation, right? Instead of a secondary, which is much more stable than a secondary. And so now the nucleophile of the chloride can go do the nucleophilic attack, and then you have the addition occur. Okay? When this alkene undergoes hydrohalogenation, the secondary carbocation could rearrange to form a more stable carbocation. So recall, oh, they did it again. It's methide. I like saying methide. Methide shift, right? When a carbocation rearrangements occur, they do occur. When a carbocation rearrangement can occur, they do occur, right? They do occur, okay? So this is just literally showing you the percentages of the last reaction that we just did, right? Double bond comes over here, pulls off the proton, okay? Leaving you with the carbocation right there. And then there's a proton, not a proton, but a hydrogen right there. Does a hydride shift to go to there, leaving you with the tertiary carbocation, right? Tertiary carbocation. And so notice that the rearrangement product, where the chlorine is, or the chloride does the nucleophilic attack, on the tertiary carbocation, there's way more of that, 60% product of that instead of the other one. If the chloride had gone and attacked over here, right? Okay, 60%. Skill Builder 8.2, drawing mechanisms on Wiley Plus. I'll meet you there. No, I'm just kidding. I'm not going to be there. But I encourage you to go there by yourselves. Okay, now let's talk about acid catalyzed hydration. The components of water, which are hydrogen and HO, right? OH, right? Are added across pi bonds. Okay, and this can be done with using an acid catalyst, right? And again, it follows the Markovnikov regioselectivity. Okay, so here we have H3O, the hydronium ion. Of course, it's a hydronium because it pulled off a proton from some acid. Okay, and when it goes through its reaction, it adds on a hydrogen right there, where it's the got the most hydrogens on that carbon, and the OH goes on the more substituted carbon, right? Just like Markovnikov addition. Okay, just like Markovnikov addition, because we have two methyls right there. 90%. Okay, so sulfuric acid is commonly used as an acid catalyst, right? And that's where the water got its proton here to become H3O. Okay, good stuff. Good stuff. So the OH is added to the more substitute carbon of the alkene, which we already established that. The more substitute carbon atom is faster react. The more substituted the carbon is, then the faster the reaction. Okay, so notice here, when we do the double bond, we lose the double bond. We have a primary, and reaction rate's only 1. And then when we do we lose the double bond here, we get a secondary, 10 to the 6th, and then we have a tertiary here, and we get 10 to the 11. Oh, sorry, my head's in the way. 10 to the 11, right? So the data is consistent with a mechanism that proceeds through a carbocation intermediate. Okay, carbocation intermediate. Hydration mechanism, right? So let's talk about the mechanism of this acid catalyzed reaction. Okay, and it's pretty much the same as the other ones. So let me come back here. All right, the double bond comes over, pulls off the proton from the H3O positive, the hydronium ion. Okay, leaving you with a tertiary carbocation there, and then the water can come over and do a nucleophilic attack on the carbocation, right? But now you have water attached to that carbon, right? So how do you get the OH instead of the water there, right? Well, I mean, you still had the other waters floating around in there right there, so it can deprotonate it. And I'm sure it's going to show it on the next reaction. Let's see. Yeah, see, right there. I'm so glad, because I was going to draw in the previous one, but if it's already going to be there, then it's going to be there, right? So water comes over with its oxygens and lone pairs, pulls off that proton, restoring the empty orbitals on the oxygen, and so now you have an alcohol, right? And that's the basis of the mechanism for a hydration reaction, acid catalyzed. Okay? Good stuff, good stuff. So we can actually do some exploitation of Le Chatelier here, right? Which sounds kind of mean, heinous, but it's not really that bad, right? So the reactants and the products of a hydration are in equilibrium, okay? And so what you can do is you can use Le Chatelier's principle to control that equilibrium, right? So if you want to make an alcohol out of an alkene, right? You can actually use diluted sulfuric acid, right? Diluted sulfuric acid with more water, right? And you'll get an alcohol. But if you want to make an alkene out of an alcohol, you just add in concentrated sulfuric acid, right, and less water, and then you get your alkene and water out of it, right? Good stuff. So just to reiterate, if we are synthesizing an alcohol from an alkene, we can use excess water, right, which dilutes the acid. But if we're synthesizing an alkene from alcohol, if we were synthesizing an alkene from alcohol, we would use okay, that's correct. I thought I was saying it backwards. I gotta make sure these things. So many typos sometimes. Okay, so just to reiterate, if we are synthesizing an alcohol from an alkene, we would use excess water, right? And we use excess water because that would dilute the acid. Okay, and that would get you your alcohol from the alkene. And if we are synthesizing an alkene from water, synthesizing an alkene from an alcohol, then we would use concentrated acid, less water, not add water any at all, and then we would get the water and the alkene. Good stuff. Good stuff. Stereochemistry. Doesn't it suck when you have to figure out what the major and minor product is of stereochemistry in the stereochemistry of these reactions? God. But it turns out, look again, 50-50. right? The stereochemistry of hydration reaction is analogous to hydration for the same, excuse me, for the same reasons. If a new chiral center is formed, a mixture of R and S is obtained. And that mixture is a 50-50 reaction, right? Or 50-50 mixture, okay? It's racemic. Remember what racemic meant, right? Racemic means a, excuse me, 50-50 mixture of enantiomers, right? And generally, separately, those R and S are optically active, but even together they're optically active, right? But then when they're together in a 50-50 mixture, the rotation of the angle of the light that's being shot, right, that goes through them, right, is 0, because the R version will go a certain number, or not the R, but one version. It's dependent. There's no connection between R and S and positive negative. It just depends on the molecule, but one configuration will have the rotation go a certain number of degrees positive, and the other rotation will have the number of degrees go negative, but they're the same number of degrees. So if you have a 50-50 mixture, it cancels each other out, and you have 0 degrees of rotation in the light. Just a quick review for you about optical activity. Okay? Racemic mixture, great stuff. You don't have to pick which one's the major or minor product, right? Practical Skill Builder 8.3, drawing the mechanism, Wiley Plus. So there's another reaction we need to talk about. This is the oxymercuration and demercuration. Okay. Markovnikov hydration, excuse me. Markovnikov hydration using water and sulfuric acid is limited. Has limited applications because rearrangements can occur, often leading to a mixture of products, right? But if you have oxymercuration and demercuration, it's an alternative, and you'll get your Markovnikov addition of the H and the OH, right? And no rearrangements will occur, okay? And let me just bring myself back to full screen power. And there we go. Remove my head right there, right? Here's our alkene, and if we do the oxymercuration here, we'll get the mercuration here, right, of the alkane now. Right, instead of having a proton there, it's going to be this guy, right? And then we can do a demercuration, and we'll get our product out. Okay, why is it that oxymercuration, demercuration is a good alternative to do Markovnikov addition of H and O? Right, it's because we don't get any rearrangements, and this is why. I'll show you. I'm surely the next slide shows you why. Let me bring myself back. Yes, here we go. So the mercuric ion, right, is a Lewis acid in this reaction instead of the proton, right? It's Lewis acid instead of the proton. So here's your mercuric acetate, which is the thing that you saw on the previous slide, and then you get the mercuric ion, the mercuric cation, and that's what's going to be the reagent in here, okay, in this reaction. So, in a normal hydration reaction, right? Again, the double bond comes over, pulls off the proton, okay, and pulls the proton, and then you get the carbocation there, right? And you get the hydrogen added, right? The carbocations will rearrange if they need to, right, to be more stable, but if you use the I forgot what it's called. I just had it on the previous slide. Oh man, I have a story about mercury that just would blow your mind. That happened to me one time. Well, I'm not going to talk about it now. Someone said I get to like tangential and start like going off on tangents, and it gets disconcerting or something confusing. So anyway, I just went back here to remind myself what the name of this ion is. The mercuric ion, cation. Okay. So if you use the mercuric cation instead of a proton, right, you can still do the same kind of thing here, where the pi bond will do an attack on the mercuric cation, just as if it were a proton. Okay. And then now, the double bond has now formed that single bond between the mercuric cation, right? But the interesting thing about it is that mercury is a metal, right? And mercury has this extra pair of electrons right here, and it will go over and donate and share some electrons with the carbocation that is formed once the double bond leaves, right? And since that mercury is there, and mercury is capable of multiple bonds, it can sit there and hold this in place, just like that, right? So that there won't be a rearrangement of any of the carbocations, okay? Because it stabilizes it, right? The mercury stabilizes that carbocation right there, right? So, let's take a closer look. The mercurium ion. See, this is why I get confused. Here it's called the mercurium ion, and previously in the other slide it was called the mercuric ion. I don't know. All you need to know is that there's a mercury there. Okay. There's so many different names, and see the thing about it is that when I went into chemistry and I got my degrees and all that stuff, they were like there was like a transition between old professors and new professors, and I had a mixture of both, and they were both using common names, old school names, and IUPAC names, and it just gets very confusing what the names of these things are. Anyway, so you can see here then that the mercury, right, is stabilizing the carbocation, right, and so there's no rearrangement. So the carbocation stays where it is, so that the nucleophile can come over and do the nucleophilic attack, right? Then mercury's electrons that we're sharing there, stabilizing the carbocation, goes back to the mercury, and it's happy-go-lucky, right? And now you have your nucleophile added to that carbocation, the original carbocation, and there was no rearrangement that can occur, right? So generally, sodium borohydride is used then to replace the mercurium ion, right? Mercurium ion with a hydrogen via free radical mechanism. Okay, and we're not going to go over any radical mechanisms right now because that's later in this lecture, in this semester. So this is just a way. Long story short, this is just a way using this mercurium ion or mercuric ion or whatever, right? Using that ion to make a Markovnikov addition, right? And prevent any carbocation rearrangement. Because if you were to do it with just water and acid, it would be it would go through a carbocation rearrangement if it could. Okay. So oxymercuration, demercuration comparison with hydration, right? The two reaction sequences provided the same. The two reaction sequence provides the same product as the acid catalyzed reaction, but without rearrangement, which is what I just said, right? So here we have the water with H3O and sulfuric acid doing an arrangement, right, doing a addition across a double bond, and you have a mixture of no rearrangement and a mixture of rearrangement, right? A mixture of rearrangement because it wants to move over here to get the carbocation right there, okay? To get the carbocation right there, and so that's where the nucleophile is going to attack. But if you were to use the mercurium ion, right, mercurium ion, instead, and it forms that cool little triangle there to stabilize that the carbocation that's there, right? Then you get 94% of the non-rearranged Markov addition, right? Right, so it won't move over here like it did up here because it didn't have to move that carbocation. The carbocation will stay on that carbon there. Okay. Practice with conceptual checkpoint 816, 817. Predict the products on Wiley Plus. So another reaction to talk about: hydroboration. Hydroboration reactions. Hydroboration oxidation adds hydrogen atoms and OHs with an anti-Markov regioselectivity. Okay. So previously we were doing the other addition with the acid base, the acid catalyzed, and with the mercurium ion, whatever, right? And that was doing a regular Markov addition. So now with hydroboration oxidation, we can do the adding of a hydrogen and an OH with anti-Markov regioselectivity, right? And we do that with a couple of things here. We have boron trihydride here, or borane, as some people call it. I think most people call it borane, but I like to call it boron trihydride. Okay. Then we have here THF is tetrahydrofuran, I believe. Okay, tetrahydrofuran. Okay, hydrogen peroxide and some sodium hydroxide, and so there's some hydrogen peroxide there. So that's why you're going to get the anti-Markovnikov addition this time. So the less substituted vinylic position, of course, will be the one that gets the substituent, right? The OH. In contrast to the Markovnikov addition we were just talking about, where it was the more substituted carbon position that got the OH. Okay, so 90% of the time here we get anti-Markovnikov addition with the OH at the least substituted carbon. Right. Note that this is a 2-reaction sequence. Okay, so let's go through this. Let's not go through this actually. Hydroboration oxidation is also stereoselective, right? But get this. Again, brings me back to the nightmares of regioselectivity, stereoselectivity, and stereospecificity of the last chapter, right? But look at here, OH and H, or H and OH, are always going to be added in the syn fashion, right? Which means that whatever happens, okay, you'll get enantiomers, okay, but like a mixture of enantiomers in this reaction, right, with H and OH, but when they get added, they're always going to be on the same side, okay? They'll always be on the same side, which is what syn means, okay? So here you have the H and the OH all pointed up at you, and then it's enantiomers where the OH and H are actually pointed into the piece of paper, okay? Anti-addition is not observed. Hallelujah. Hallelujah. Because now you don't have to choose, right? You don't have to say, which products are going to be here, okay? Tell me if the products are going to be the syn addition or the anti-addition, which is the major product, right? So, geometry and hybridization of boron trihydride, right, or borane, is actually analogous to the carbocation, right? So we have here a tertiary carbocation, you see, and here is boron trihydride, and the p orbitals line up like almost exactly the same. They're analogous to each other. Cool stuff. Right? So the boron atom does not have an octet, right? So boron trihydride forms a dimer to help fill boron's octets. Okay? So literally what's happening here is that we're going to have two boron trihydrides or boranes come together, and they're going to share two hydrogens with each other. It's not going to be like a permanent bond, but it's kind of like an association. Okay? Right? And so this resonance hybrid reveals a 3-center 2-electron bonds. Right? So 3 atom centers, 1, 2, 3, with 2 electron bonds. Right? Spread over 3 atoms. That's kind of cool. So we call that a dimer, by the way, when there's like a loose association with 2 molecules that are exactly the same thing. Right? Good stuff. So now the dimerized boron trihydride, right, or borane, can be stabilized by using an ether solvent, so that appreciable amount of borane is present, and so the active borane is there with THF, this is THF right here, right, the ether solvent, okay, tetrahydrofuran, I believe it's called. Yeah, tetrahydrofuran. Okay. The electrons from the oxygen over here of this ether come over, right, and stabilize stabilize the empty p orbital right there, and you get the tetrahydrofuran boron trihydride structure. So what happens then is that hydroboration actually follows an anti-Markovnikov regioselectivity. Okay. What that means, again, just to reiterate, right? The less substituted hydrogen carbon attacks the boron. Excuse me. And the more substituted carbon develops a partial positive, which triggers the hydride shift. Okay. So let's take a look at what this looks like here. We have our alkene right there. Okay, we have our alkene right here. And so it doesn't show it here, so I'll have to draw it myself. The double bond comes out and attacks the boron, like that. Okay, and that's what this double bond, this dotted line is right here. Okay, and then there's a hydride shift where the hydride comes from the boron and goes over here and shifts over to the carbocation. So you get a transition state, right, where there's association between the carbocation and the hydrogen and the boron still associating with the what used to be the double bond, right? And then we get our product, which is the boron dihydride, right, attached to what used to be the alkene, but now is an alkyl, right, the alkane with the hydrogen there. And of course, this is the anti-Markovnikov, right, because the boron here attached to the side, the carbon that had the least amount of substitution, right, those are two protons or two hydrogens there at that carbon, whereas the hydride or the hydrogen went and added itself over to the carbon that had the most substitution, that had the two methyl groups. Okay, so recall that the more substituted carbon will be the better at stabilizing a partial positive charge, right? Which is the basis of the stability of a tertiary carbocation. They could have just said that in that line. I don't know why they didn't say that. Okay, so again, just reiterating, hydroboration follows anti-Markovnikov regioselectivity, right? So the interesting thing about this is that boron boron trihydride reacts with 3 equivalents of alkenes. Okay, so you do this 3 times, and you'll get, you do this 3 times, the same boro trihydride, right, that just lost one of its hydrides to the alkene, right? That same one does this thing 2 more times, and then you get a trialkyl borane, right? You get a trialkyl borane with borane in the center, right? That's why it says right here, first step is repeated for each of the boron hydrogen bonds. Okay. Okay. So the sterics also influence the regioselectivity, right? When you have the transition state in the anti-Markovnikov addition, right, the carbon that lost its double bond and gave it over to and attacked the boron with it, right, is there, and then the hydrogen is doing the hydride shift is occurring right there, where it's stabilizing the carbocation right there, and also still associating with the boron, right. There's a lot of room there for this to happen. But if you were to switch it around, where the if you were to switch it around to the Markovnikov way, right, the Markovnikov addition way, then this would be where the hydride would be trying to shift, okay, and then this would be where the carbon would be doing the attacking of the boron, and now you have all this steric hindrance right here, and that's why that doesn't happen. That's why hydroboration follows anti-Markovnikov regioselectivity. So let's just go through this mechanism, right? We start off with hydroboration here, okay, where we have that loose association between the hydrogens of the boron and the carbon with the boron, right there, right? We do this 3 times, and we get the trialkyl borane, okay? triethylborane. But then there's an oxidation mechanism. Okay, there's an oxidation mechanism, right? And what happens is that you can have a hydrogen peroxide come over, and a hydroxide ion can pull off a proton from the peroxide, right? And so now you're left with the peroxide anion right here. What is that called? Hydroperoxide. The hydroperoxide anion. Okay. The hydroperoxide anion now can do a nucleophilic attack on the boron of the borane, the trialkyl borane. Okay. And now the peroxide is attached to the trialkyl borane. Okay. Rearrangements occur, right? And so the one of the alkyl groups will come over and rearrange itself, so it attaches itself to the first oxygen, and that makes it so that we lose a hydroxide, right, which is right there. And now we have this structure here, okay? So it's no longer a trialkyl borane anymore, okay? Because now it has a oxyborane on it, okay? This will happen two more times with this one and this one, giving you the product of the trialkyl oxyborane. Hydroxide comes over and does a nucleophilic attack on the boron. Okay. And then, once it does that, one of the alkyl groups will fall off, right? Will leave as a leaving group. The alkoxide will leave as a leaving group, right? And then, when it leaves as a leaving group, it can pull off a proton off of a water, giving you an alcohol. So using hydroboration and oxidation, you can go from this alkene here, right? That alkene here, with borane, and do a synthesis and come up with an alcohol at the end. Good stuff, right? Multi-step right there, multi-step mechanism. So hydroboration, oxidation, stereocyclicity. Oh, thank God. This is also a syn addition. You don't have to worry about knowing whether it's syn or anti. It's syn addition. Hydroboration is stereospecific, yes, but it's only syn addition. Okay. If only one chiral center is formed, a pair of enantiomers is formed by addition to either face of the alkene. Okay, either face of the alkene. Excuse me. So you can get it. You can get the OH on the top side, or you can get it on the bottom side, right there. Again, hydroboration is stereospecific only in the syn addition occurs. Okay, so if there's two chiral centers formed, then a pair of enantiomers is obtained, right? And so notice here, the hydrogen and the OH are all on the same side. The hydrogen and the OH are on the same side, but they're both syn, right? There's no anti. That's the big thing out of that, okay? Because this guy had two chiral centers. So let's predict the product of this guy right here, real quick. We're gonna do. So remember that it's all syn addition, right? So, and I give myself a lot of room here for some reason. I don't know why, but that's okay. It's always the hardest part for me is drawing the pentane, the cyclopentane. So I draw the cyclopentanes first, right? Like that. Okay. And so the first one here, right? Since the double bond is over here, and that's the thing that's going to be doing the attacking on the boring. Okay. And it has to go 3 times, so I don't want to draw out the mechanisms, right? You saw the mechanism already before on the previous slide. But the product we'll get from this is this stays the same, right? Nothing happens to that, because that's not even going to be involved on either, because that's going off from the double bond, right? But what will change is that methyl there, because it's on one of the addition sites, okay? And it's on the addition site of for anti-Markovnikov, right? So that means then that we'll have an OH coming out of going into the paper up here, right? But since it's always a syn addition, we'll also have a hydrogen over here on the same side, okay? And since this hydrogen here is already going to the back of the page, and we already have multiple 2 bonds here in the plane of the page, that means then that the methyl group that was here, right, will come out of the page like so. The second product will do the same thing, except this time the OH comes out of the page instead of going into the page like the last one. Same thing is true of the hydrogen coming out of the page there. So, but what's going to happen to this methyl group now? Well, since this one was coming out, that means this one's going to be going into the page this time, just like that. And those are your 2 products from this reaction. Fun stuff. Oh crap! Didn't even realize that it's going to show the answers here, right? Am I right? I think I was right. Yeah, I am right. See? So we have the OH there going into the back of the page, and the hydrogen here going into the back of the page, right? And then this comes out, the methyl comes out of the page, right there. And then here we have the OH going out of the page with the hydrogen going out of the page, and then we have our methyl group going to the back of the page. Right, I think it's the exact same thing I drew. Yeah. Yep, that's exactly what I drew. Oh, and that ends today's lecture. So you get a little bit of a break today. There are not any assignments or quizzes that are going to be assigned in lecture today, right? Because we're not finished with this chapter yet. And quizzes won't be until Tuesday, okay? But there is a reminder that you do have an exam 4 on Friday, June 25th, 2021, okay? All right, I'll see you guys in the exam solutions video, and then also tomorrow for the conclusion of the addition reactions of alkenes, okay? Have a good day.